Understanding the difference between deep learning and reinforcement learning. 1. Definition of deep learning. Deep learning is a subset of machine learning that utilizes artificial neural networks, ANNs, to learn and make decisions from large amounts of data. It is inspired by the structure and function of the human brain, using multiple layers of interconnected nodes, neurons, to process and extract features from raw data. Deep learning algorithms are capable of automatically discovering patterns and representations in data, enabling tasks such as image and speech recognition, natural language processing, and autonomous driving. 2. Neural networks and architecture. Deep learning models are characterized by their deep neural network architectures, which consist of multiple hidden layers between the input and output layers. Each layer extracts higher-level features from the input data, learning hierarchical representations that contribute to the model's ability to generalize and perform complex tasks with high accuracy. 3. Training paradigm. Deep learning models are trained using supervised, unsupervised, or semi-supervised learning paradigms. In supervised learning, models are trained on labeled datasets, where input-output pairs are provided to learn mappings between input features and target outputs. Unsupervised learning involves training models on unlabeled data to discover underlying patterns and structure. Semi-supervised learning combines both labeled and unlabeled data for training. 4. Applications and use cases. Deep learning has revolutionized various fields, including computer vision, e.g., image classification, object detection, natural language processing, e.g., language translation, sentiment analysis, healthcare, e.g., medical image analysis, disease diagnosis, finance, e.g., fraud detection, stock market prediction, and robotics, e.g., autonomous navigation, robotic control systems. 5. Definition of reinforcement learning. Reinforcement learning, RL, is a machine learning paradigm where an agent learns to make decisions by interacting with an environment. The agent receives feedback in the form of rewards or penalties based on its actions, with the goal of maximizing cumulative rewards over time. RL is inspired by behavioral psychology, where learning occurs through trial and error and reinforcement from the environment. 6. Agent-environment interaction. In reinforcement learning, the agent takes actions in an environment, observes the resulting state and reward, and learns to optimize its decision-making strategy, policy, to maximize long-term rewards. RL algorithms learn through exploration, trying new actions, and exploitation, leveraging known actions with higher rewards, balancing between learning new behaviors and exploiting existing knowledge. 7. Training dynamics and algorithms. RL algorithms include model-free and model-based approaches. Model-free RL directly learns optimal policies from experience without a model of the environment dynamics. Model-based RL constructs a model of the environment and uses it to plan actions and learn policies. Popular RL algorithms include Q-learning, deep Q networks, DQN, policy gradient methods, and actor-critic models. 8. Applications and use cases. Reinforcement learning is applied in autonomous systems, e.g., self-driving cars, robotics, game playing, e.g., AlphaGo, recommendation systems, e.g., personalized content delivery, resource management, e.g., energy optimization, and real-time decision-making tasks where learning from interaction and adaptation to dynamic environments are crucial. 9. Challenges and considerations. Deep learning and reinforcement learning face challenges such as scalability with large datasets, computational complexity, interpretability of results, and ethical considerations regarding bias and fairness. Advances in hardware accelerators, e.g., GPUs, TPUs, algorithmic improvements, and interdisciplinary research continue to drive innovations in both fields. 10. Integration and future directions. The integration of deep learning and reinforcement learning holds promise for developing more intelligent systems capable of autonomous learning and decision-making in complex real-world scenarios. Future research aims to enhance the robustness, efficiency, and interpretability of AI models while addressing societal impacts and ethical implications of AI deployment.